All right, hello everyone. Today we're going to be solving LeetCode 875 Koko Eating Bananas. So first we're going to read the problem statement. So Koko loves to eat bananas. There are n piles of bananas, and the ith pile has piles I bananas. The guards have gone and will come back in H hours. Koko can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. And if the pile has less than K bananas, she eats all of them instead and will not eat any more during this hour. Koko likes to eat slowly, but still wants to finish all the bananas before the guards return. Return the minimum integer K such that she can eat all the bananas. All right. As we can see, with piles 3, 6, 7, 11, and the guards come back in 8 hours, the minimum banana per hour speed Koko can eat at is 4 bananas per hour. And we're going to quickly explain why this is the answer, and then we're going to go into explain how to solve the question and then straight into the code. All right, so the output is clearly 4 here because we know the answer, but let's say we didn't and we tried a different number. Let's say we tried a rate of 6 bananas per hour. So how would we calculate how long it takes her to finish this entire pile? Well, we know that since she can eat 6 bananas per hour, she would spend 1 hour on the first pile because there's only 3 bananas, 1 hour on the second pile, 6 bananas. But this is where it gets a little interesting. She would actually spend 2 full hours on the third pile because in the first hour she would finish 6 bananas and there would be 1 banana left. But she has to finish the whole hour, so she'd wait again, eat 1 banana, and wait a whole entire hour before moving on to the next pile. And same thing for 11. She would finish 6 in the first hour and then 5 in the next hour because she can't move on to another pile until that hour has commenced. So as we can see here, if we accumulate all of these, this would be a grand total of 6. So with a banana eating rate of 6 bananas per hour, she could finish the entire pile in 6 hours. But as we see, we have a total allotted time of 8 hours. So we want to know, can we do better? So we should try a slower banana eating rate because we know that 6 works, but we have more time to spare. So let's see what happens when we try 5. Same thing here. We say it would take 1 hour, 2 hours, 2 hours, and 2 hours. So 2, 4, 6, 7. So it takes 7 hours at an eating rate of 5 bananas per hour. We still have 1 more hour that we could play with. So let's go down and see, does another answer work? Well, we know the answer is 4, but let's just try it out. It would take 1 hour here, 2 hours here, 2, and it would take 3 hours to finish 11 bananas because the first hour she eats 4, second hour she goes up to 8, and then the next hour she eats the last remaining 3. So 3 hours. So 3 plus 2 is 5, plus 2 is 7, plus 1 is 8. So with a banana eating rate of 4 bananas per hour, she can finish all the bananas in 8 hours, and that's the allotted time we have. It's actually equal to the time the guards come back, and that's the answer. Because if we went any lower, it would spend too much time to eat the bananas. And let me just quickly go over it. So let's say we tried 3. It would take 1 hour here, 2 hours. She would eat 3 hours here because 3 on the first hour, 6 on the second hour, and then the last 1 on the third hour. And it would take actually 4 hours to finish all of these. So 4 plus 3 is 7, 8, 9, 10. So it would take her 10 full hours to finish the bananas at an eating rate of 3 bananas per hour. But we only have 8 hours. So the guards come back 2 hours before she finishes. So that's no good. So the answer is 4. So we're going to go over how would we actually think about this question and solve it ourselves. Well, this is a binary search question. So in questions like these, I like to think about what is the range? What's the minimum amount of bananas that she can eat? And if we think about it, it would be 1. The minimum banana eating rate she can eat is 1 banana per hour. She can't eat 0. And what would be the max? If you think about it, the max would be whatever the max is in the piles. Because let's say she ate at a banana eating rate of 11 hours per hour, 11 bananas per hour, she would finish the entire pile in whatever the length of the array is. Because she ate 11 bananas per hour, all these would only take 1 hour to finish. So the maximum that she can eat at is 11. So 1 to 11, our answer is somewhere in between this. So what I like to do is create like a number line to help visualize what we're going to be doing here. So I'm going to quickly write that. All right, so here we have our number line. And in classic binary search, if you're new to binary search, I recommend solving the easy binary search question first. This is a bit more advanced, but we always want to find our midway point. So let's say our left pointer is at the lowest bound and our right pointer is at the highest bound. What we want to do is find the midway point. So we just calculate what's 1 plus 11, that would be 12, and then divided by 2 to find the midway point. That would give us 6. So our midway point is 6. We want to check, how long does it take Koko to eat all the bananas at an eating rate? Because M represents the eating rate per hour that we're looking at here. So as we already recalled, when we tried 6, it took her 6 hours to eat all the bananas. So let's say that's a possible answer, 6 bananas per hour, and it took her 6 hours to finish all of them. And how we calculate that is, what we're going to do is use the ceiling function. We're going to iterate through the piles of bananas and use math.ceiling divided by the pile divided by the eating rate we're looking at. Because as we see, let's say we eat it at a banana eating rate of 6 bananas per hour and we get to the 11. 11 divided by 6 would be like what? 1.9 something, but we have to round up because she only eats in 1 hour intervals. And same thing here. Let's say we look at the 7. 7 divided by 6 is like what, 1.1 or something? But she can't eat, and she only can eat in 1 hour intervals, so we have to round that up all the way to 2. So that's why this would take 2 hours to eat bananas here to finish this pile. So we're gonna have a helper function that's gonna go through the banana pile and tell us how long it takes her to eat all the bananas at X eating rate, or whatever our midway point is. So as we saw earlier, we already calculated 6 in the example. It would take her 6 hours to finish all of them. And we see that that's less than the time it takes the guards to come back. So what does that tell us? That tells us that any number greater than 6, we don't even need to check, because we're looking for the minimum banana eating rate per hour. So anything greater than 6 works, but is not optimal, because we know 6 works. So essentially, what we can do is X out all of these numbers, and we've already checked 6. So what we're going to do is move our range down. We can move our right pointer to mid -1. So mid is 6, and then -1 would be 5. And our new mid will calculate that. And we're doing this because we just checked 6, so there's no need to check 6 again. And we're going to run through the same process. We say, what's 5 plus 1? That's 6. Divided by 2, that would be 3. So our midway point is now 3. We do the same calculations. We say that it would take her 1 hour to eat the first pile, 2 hours to eat the second pile, 3 hours to eat the third pile, because the first hour she eats 3, second hour she goes up to 6, but there's 1 banana left, but she has to stay the whole hour, so she has to stay another hour just to eat 1 banana. And the fourth pile, she would take 4 whole hours. And we add that all up together, and what do we get? We get 10. So it takes her 10 hours to eat all the bananas at an eating rate of 3 bananas per hour. The guards would come back by then, so that can't be the answer. So what does that tell us? We know that anything at the midway point of 3 or less can't be the answer, because if we chose any eating rate per hour that's less than 3, it would give us a greater number than 10, which is still not valid. So we know that all of these numbers are not valid. And we're going to do the same thing. We're going to move our left pointer to the next available number to check. So our left pointer would be m plus 1, because we just checked 3. So we're going to move our left pointer. It's going to travel all the way up to the 4. So now we have our left and right pointers are right here. This is what we've deduced or reduced our range to in only 2 searches. And we're going to try one last time. We say, what's 4 plus 5? That's 9. 9 divided by 2 would be 4.5, but we always round down because we only work in integers. So that'd be 4. We check 4 and we'll see that, let me quickly erase this. We check 4 and we'll quickly see that it would take her 1 hour to eat the first pile, 2 hours to eat the second pile, 2 hours to eat the third pile, and 3 hours to eat the fourth pile. We add all these numbers up. This would be 5 plus 2 is 7, and that would be 8. 8 hours is equal to the number until the amount of hours are allotted to us until the guards come back. So that tells us that is a possible answer. Any eating rate that gives us a total time that is equal to or less than h is a valid answer. Just like 6 was a valid answer, but we just found 4. So we do that, and what we're going to do is move our left pointer up to m plus 1. So our mid is actually on the same pointer as our left. So m and l are at the same point. We move l up to m plus 1, and that would be 5. So now left and right are now equal. So we've searched the whole entire range. So we'd go out of our loop, And what we want to do is check our valid answers that we found and pick the minimum one. What's the minimum between 6 and 4? We pick 4, and that would be the answer. So let's quickly actually code this up, and hopefully it'll make a lot more sense. So in binary search questions, I always want to start off with the range. So we say L equals 1 for the left pointer, and next we're going to account for R. R equals the max of piles. As you remember, the biggest number we could possibly pick is whatever the highest banana pile is. Next, we're going to have a res variable that's just going to hold our answer. And we're picking the minimum, so we want to pick a number that is greater than any number we'd see. So we can just call res R for now, or max of piles as well, because we're going to keep reducing it. And we know we won't find anything greater than max of piles, so it only has a chance to go down. Next, we're going to create our helper function. As you remember, let's say, remember when we found the midway point of 4, we had to calculate how many hours it would take her to eat all of the bananas at an eating rate of 4. But how do we do that? We need a helper function. So what we're going to do is say define function, and we're going to call it get time. And we're going to use a variable called num. And what it's just going to do is calculate the total time it takes her to eat all the bananas. So total equals 0. And we're going to say for pile in piles, total plus equals ceiling pile divided by num. And just to go over that again, just make sure we're all on the same page here. Let's say we're looking at the eating rate of 4, and let's say we wanted to calculate how long it takes to eat this fourth pile here. So what's 4 divided by 11? Let's say it's 3 point something. Let's just 3 point x, whatever that is. But we need to round up because she can't eat in decimals. She only can eat in 1 hour intervals. So you round that up to 4. And just like you see, the answer was 4 before. So that's how we calculate how long it takes to eat each pile. Next, here we have the fun part. Remember, we want to stop our loop once the 2 pointers intersect each other, because that means the valid range is closed. So we're going to say while left is less than or equal to right. And here's where we're going to do most of the logic. So we're going to first calculate our midway point. So mid equals left plus right, and then truncate 2. So just we're dividing by 2 and rounding down. So that's how we always calculate the midway point. Next, we're going to have a variable called time, and that's just going to be equal to whatever our midway point, because our midway point represents a banana eating rate per hour. And time is going to represent how long it takes her to eat all of the bananas at that eating rate. So time equals get time from our helper function, m. Now, this is where the interesting part happens. This is where we move the pointers, so pretty much the meat and potatoes of the algorithm. So let's say if time is greater than h, which is our allotted time until the guards come back, what does that mean? Remember when we looked at 3 and it took her 10 hours to eat the bananas? That means anything less than 3 or equal to 3 is not a valid answer. And we move the left pointer to mid plus 1. So that's exactly what we're going to do here. We're going to say left equals mid plus 1. And we say the next one be if time is less than or equal to, because we only want to deal with numbers that are less than or equal to the allotted time, which is h, because those are only valid answers. So if it's a possible valid answer, we want to say res equals the minimum of res and m, because m is our eating rate per hour. And this should always return the minimum. And next we want to move our pointers. So right will just equal mid minus 1. And we're doing that because if we find out that the midway point is a valid answer, everything greater than the midway point would give us a less efficient answer, so we don't have to check that. That's why we're moving the R pointer to mid minus 1, because we just checked mid. And all we have to do next is return res. And hopefully this should work. We didn't mess up at all. Let's see. First try. Oh, we calculated the total, but we didn't return the total. So remember, in our helper function, we calculated the total, but at the end of the helper, we never returned it. So I think that's the small issue. There we go. Wait, let's submit and let's see what happens. And there we go. We solved the question. It's actually pretty efficient. We beat 95% of runtime and 83% in memory. So I hope you enjoyed the video. Peace.